This is our common source amplifier using current mirror bias. Now it behaves largely like the common source amplifier that we already know, but we will put down the small signal picture of this and analyze it. And also we want to derive the constraints on the capacitors C1 and C2 and the resistor RG. Okay, that will do. Now in the incremental small signal picture, this VDD becomes a short circuit because there is no change in VDD. Vs will be the only source remaining, and this current source I0 becomes an open circuit because there is no increment in the current source itself. This I0 and VDD are parts of the operating point, and this Vs is the increment. Okay. So if I do that, we have to draw the incremental equivalent of this. First, let me draw it for the core components of the common source amplifier. Okay. There is something else connected to the gate that I'll add on later. So here we have Vs Rs and C1, and we have the small signal equivalent of the transistor M1. Okay, if this is M1, I'll call this GM1 VGS1, where this is VGS1, and we have the resistor RD, AC coupling capacitor C2, and load RL. Okay. By the way, in all these analysis, I am neglecting the incremental output conductance of the transistor itself. But we know that it appears between drain and ground, so eventually it will appear in parallel with RD and RL. Okay. So if you do want to analyze it with the output conductance of the MOS transistor, it's not at all difficult. So I'll keep it simple and I'll omit it for now, but please realize that it will simply appear in parallel with these two. So wherever you had RD parallel RL, you would get RD parallel RL parallel RDS. Okay. Now we have something else connected to the gate of the transistor, that is this point, that is this part of the circuit. Okay. Now what is that? From the gate of M0 to M1 we have RG. Okay, so let me also label these. This is G1, D1 and S1, meaning that they are gate, drain and source of the MOS transistor M1. Now I will have the transistor M0. So I have GM0, VGS0, where this is VGS0 and this is gate of transistor M0, drain of transistor M0 and source of transistor M0. Okay, and the drain and source of M0 are connected together, so that connection we have to show. So please be very careful while putting down the incremental equivalent circuit of a given circuit, because if you make a mistake there in some connection or by omitting or wrongly connecting some component, the results will be completely wrong. Okay. So this is the new part here. Okay. So what we have is this part, this RG in series with something here that's connected to the gate of the transistor. So let's examine this itself to see what it looks like. That is, we want to find out the incremental equivalent of this part between this gate 1 and through this RG in series with this whole component. Okay. What we have is RG connected to gate of M0, and we have GM0, VGS0, where this is VGS0, and we have the drain and gate connected together. Okay. So between these 2 points, between this point and ground, it's a 2-terminal device. That is, this part is a 2-terminal device, and that can be analyzed by itself. We can also analyze it from here, but what we see is a general result. So let's do this. So this is G0, D0 and GM0, VGS0, where this is VGS0. So now let me apply a test voltage here, V test, and find the current flowing I test. What is it? Extremely easy to analyze. This V test itself is VGS 0, right? So VGS 0 equals V test. So this current here is GM 0 times V test. Okay. So this I test, it consists of only this current. Okay. So I test will be GM 0 times V test. So the small signal resistance seen between this point and ground is nothing but V test by I test equals 1 over GM0. Okay. So this whole thing here between this one and that one has an incremental equivalent whose conductance is GM0, or the resistance is 1 over GM0. Okay. This is in general true for a transistor whose drain and gate are connected. Okay. So if you have a transistor like this, and since we consider positive threshold voltages, this will be in saturation region. The equivalent between these two for the incremental signal is a resistor of value 1 over GM0. Okay. Now the equivalent from here is very obvious. It's RG in series with 1 over GM0. Okay. So that's the resistance that we have. So now we can replace this entire thing here, the part due to RG and M0, with a single resistor whose value is RG plus 1 by GM0. Okay. Now in a practical common source amplifier, this 1 by GM0 is likely to be much smaller than RG, so it can be neglected. But still, this result itself is useful to remember because you will encounter this in many other situations. When you have a transistor in saturation with its gate connected to the drain, you will have these two terminals, and between them you will see an incremental resistance which is 1 over GM0. Okay. Now once we have this equivalent circuit, this picture looks exactly like our old common source amplifier with constant voltage bias. Okay. So we can simply use all of the results from that one. Okay. Okay. So I'm not going to rederive the conditions. So for C1 to appear like a short, the constraint is that the reactance of the capacitor C1, 1 over omega C1, must be much smaller than whatever appears across it after the source is nulled. That is, Vs is set to 0, so this becomes a short circuit. And what appears across it, if you complete this ground connection, it becomes obvious. It's Rs and this resistance in series. Okay. So 1 over omega C1 must be much smaller than Rs plus Rg plus 1 by GM0. Okay. Similarly, for C2 to appear like a short circuit, it should be such that its reactance is much smaller than whatever appears across it, and with the source nulled, this current source becomes an open circuit, so this is not there, and what we have are just Rd plus RL, exactly the same result we had from the original common source amplifier. Now there is an alternative criterion for C2, as we know, that is to make sure that this drain voltage and the load voltage are exactly the same in the incremental sense. So if you want to have that, then 1 over omega C2 must be much smaller than RL. Okay. Now finally, if we satisfy these conditions, then we can replace both C1 and C2 by short circuits. Okay. They are replaced by short circuits. Then what is the voltage that appears as the gate source voltage here? we know that VGS1 by Vs is this resistive division. Okay, you have Rs here and this resistance Rg plus 1 over Gm0. Okay, so this ratio is Rg plus 1 by Gm0 divided by Rg plus 1 by Gm0 plus Rs, and we want this to be approximately 1. So if this has to be approximately 1, then we need Rg plus 1 by Gm0 much more than Rs, or in other words, Rg must be basically much more than Rs. Okay, because 1 over Gm0 is likely to be much smaller than any of these resistances. So I went pretty quickly through this. This is because we've already worked out the results. Okay, so because if you recall, in case of the original common source amplifier, instead of this quantity, what did we have? We had R1 parallel R2. Okay, and these were exactly the same as before, and we also had a condition similar to this, which was to say that R1 and R2 both must be much greater than Rs. Okay, so these conditions are exactly same as for the common source amplifier. So I hope that is quite easy to understand. Okay.